Хорошо, сейчас я тогда...
Ага, да, и я сейчас вот, ага. У вас уже
Хорошо, мой,
есть.
мой
Есть,
файл
да.
виден?
Видно, видно, да. Ну вот сегодня у нас выступает Тимур Охберг. Today's speaker is Timur Oikhberg from the University of Illinois, and the title of his talk is Some Finite Dimensional Problems of Phase Retrieval in Banach Lattices.
Mhm.
Please.
Okay, so thank you very much for the introduction. So I must warn all the listeners that I will be speaking in English, and part of the reason is that I'm not really familiar with the phase retrieval terminology, how it works in Russian. And I should also say that this is a joint work with D.Freeman, B.Pineau, and M.Taylor. Some of the results that I'm going to mention have already appeared. Some of them will hopefully be posted at some point, hopefully soon. And also, I would like to maybe preventively apologize that I spoke on a similar topic on this very seminar almost 2 years ago. So some of the slides may appear familiar, some of the results may appear familiar. So please bear with me, and because eventually the talks will diverge. So it's not like
We
the
exaggerate
rerun.
our memory.
Okay. So to begin with, maybe I should start with elementary definitions. All pretty much all the Banach spaces and Banach lattices that I'm going to talk about today, are going to be real as opposed to complex. Um, somehow there are maybe two reasons for this. One reason is that uh, also is that uh, real Banach lattices are better studied and they behave nicer uh, than complex Banach lattices, and also there are some results of which we know in the real setting, but not in the complex setting. So in any event, so a real Banach lattice is a real Banach space which is equipped with order, and this order is consistent with addition and multiplication by non-negative scalars. Um, and we can also perform lattice operations, meaning that the max, the least upper bound of any, well, here I wrote any two elements, but this can be also done for any finite collection of elements. And likewise, the mean, the greatest lower bound. And finally, the norm is a lattice norm. It is consistent with the order, meaning that if we have two elements such that the modulus of one is dominated by the modulus of the other, then we have also the corresponding inequality for norms, and the modulus is just the maximum of the element and its opposite. Uh, so some examples are, for instance, the C of K spaces, the LP spaces, the Lorentz spaces, the Orley spaces. So note that all the examples that I'm given here are function spaces, and in fact, if your intuition in Banach lattices is not very strong, then you can just visualize a Banach lattice as a function space. So think of a function space with pointwise operations. And pretty much everything you can say about function spaces will be true for Banach lattices as well. So throughout the lecture, I will first of all need the notion of disjointness. So two elements are disjoint if the minimum of their moduli is zero, and this, like again, if you think of a function space, well, if the minimum of the moduli of two functions is zero, this this would mean that they have disjoint support. So this is what this definition reflects. And also we'll probably need the fact that any element in a Banach lattice can be represented as in a unique manner as a difference between its positive part and negative part. So the uniqueness comes from the fact that we have a difference of two positive elements which are disjoint from each other, and they can actually be calculated. Again, the way it works for Banach lattice is the way it's done for function spaces. This is part of the title was the word Banach lattice. So this is what this word means. The second part was phase retrieval. So here is the definition. So throughout X is a Banach lattice, and the subspace E of this X, we say that it does phase retrieval if whenever we have F and G in E whose moduli are the same, then F and G are the same up to some scalar, some unimodulus scalar multiple. So in a sense, this if you think of a function space, well, you have the modulus, and then you recover, say you have the modulus of F, and then you recover this F by knowing its modulus and also by multiplying it by some unimodular phase. So this is what the terminology refers to, that this unimodular phase can somehow be recovered. And we say that, we say that a subspace does C-stable phase retrieval if whenever we have F and G in E, well, the idea is that if the moduli of F and G are close to each other, then F and G are also close to each other up to a scalar multiple. This kind of inequality appearing in the definition, it may appear somewhat maybe arbitrary, but it's not, because it's easy to check that we always have an inequality in the other direction. So somehow the inequality appearing here, what it means is that if you are measuring the modulus of F, and if you make a small error of measurement and you try to reconstruct F from this erroneous measurement, then the reconstruction will be almost precise. So the error of reconstruction will be small. And the final part of the definition is that, well, so by the way, this definition here, it works in both the real and the complex setting. And in the real setting, the left-hand side is just the minimum of two norms appearing right here. And, well, I should also say that we say that E has stable phase retrieval if it does stable phase retrieval for some constant C. So what are the connections between stable phase retrieval and simple phase retrieval? So clearly, SPR, the stable phase retrieval, implies the phase retrieval. In finite dimensional spaces, which will be the focus of my talk today, the opposite is true. However, and I hope to get to this point today as well, we can only say that that in finite dimensional E, phase retrieval implies SPR, but we cannot control the constant. And trying to control it is also a topic that I will mention. And in the infinite dimensional setting, things are different because you can always find, if X is an infinite dimensional Banach lattice, then you can also always find a subspace, closed infinite dimensional subspace, which does phase retrieval, but not stable phase retrieval. Maybe before stating our results, let me try to persuade you that phase retrieval may really be useful. So I think historically it first occurred in the field of X-ray crystallography, which arose in the beginning of the 20th century when X-rays were discovered. Let's say you have a crystal. In this crystal, electrons are somehow distributed, and this distribution can be described by a certain function. And then when you scatter X-rays, you somehow this, and I mean, I'm not a physicist, so this is what I read somewhere. So essentially, you obtain after scattering, you get the Fourier transform of f, and what you measure is its intensity. So, which is the same as saying that you measure the modulus of the Fourier transform, but then you have to reconstruct f itself. And of course, you know something about f. You cannot obviously reconstruct a function from its modulus. Equivalently, you can think of it as a phase retrieval problem. You know that your f hat, your Fourier transform, lives in a certain subspace, and you know its modulus. You have to recover f hat itself. So a little bit later, quantum mechanics arose, and right actually at the beginning of quantum mechanics, Wolfgang Pauli mentions this problem that let's say f is your wave function, and you somehow know the probability density of the position and the momentum. So again, I'm not a physicist, but apparently this means that you somehow know, don't ask me how you know this, you somehow know the modulus of f and the modulus of f hat, its Fourier transform. So in our terminology, you can consider the map J from L2 to the direct sum of L2 with itself, which takes f to, the pair f hat. And the question is, does the image of L2 under this map J, does it do stable phase retrieval? And, or simply does it do phase retrieval? And actually the answer is no. The answer is no even for the phase retrieval, but it took a while to obtain this answer. And now maybe fast forward to, I don't know, the late 20th or early 21st century. And then people in approximation theory started working with frames. Let me maybe remind the definition. So let's say H is a Hilbert space, and we have a collection of vectors, xi I, and we say it's a Parseval frame if the Parseval identity holds. So if for every element xi in the Hilbert space, but this equality is true. And the question is, assume so you can actually think of those xi i's as measurements, and of course you can say, okay, so if xi I form an orthonormal basis, then it's your frame. But the thing is that sometimes you need redundant measurements. So you somehow make those redundant measurements, and you record their outcomes, and you want to recover your vector xi. So maybe to restate it in a more functional analysis form, you have the so-called analysis operator from your Hilbert space to L2 indexed by our capital I, and being Parseval, the frame being Parseval means that this operator is an isometry, and then you need this the so-called synthesis operator, which reconstructs psi. Now, of course, problems in phase retrieval often arise when either the measurements being the testing of xi against xi i's, either the measurements are somehow imperfect or somehow the results of some of the measurements erased, and the phase retrieval problem here is consists of recovering xi from the moduli or absolute values of the measurements. As I mentioned, this analysis operator A is an isometry, so instead of recovering xi, you can actually recover a xi. So translating this into our language, we ask ourselves, well, does A of H, the image of H in L2 of I, does this image of H, does it do phase retrieval? So of course the answer is that, well, you have to be careful which frame you are using. So let's see. So I hope this gives enough of a motivation, and the definition is clear. So let's see, are there any questions up to this point before I actually try to introduce some tools? No, let's move on. The question is then what are easy examples of the failure of phase retrieval? What are examples of spaces which fail the phase retrieval? And one abstraction to the phase retrieval is disjointness. So let's say we have two functions in some function space. Say f is the graph of f is in blue, the graph of g is in red. So in this situation, you can see that the modulus of f plus g is the same as the modulus of f minus g, but of course f plus g is not the modulus, is not a multiple of f minus g. So this means that if f and g are in some e, then this e cannot do phase retrieval. So what happens if you try to do the stable phase retrieval? Well, in this situation, we need to introduce the notion of almost disjointness. So first of all, the notation, S of E will denote the unit sphere of E, and we say that E contains C almost disjoint pairs, where C is some constant. If there exists F and G on the sphere, so that the minimum of their moduli is less than little c. And this phenomenon turns out to be connected with stable phase retrieval. Namely, it turns out that this almost disjointness in the real case is the only abstraction to stable phase retrieval. So specifically, there is this theorem of Belokopitov that if X is a real Banach lattice, then and E is a subset of this subspace of this Banach lattice, then this E does a stable phase retrieval with constant C, if and only if it does not contain 1 over C disjoint pairs. So as I said, and this is actually a major difference between the real setting and the complex setting, which in my mind justifies focusing on the real on the real setting. So you can see that if you have two almost disjoint elements in some subspace, then the subspace cannot do stable phase retrieval. And this is true in both the real and the complex case. But in the complex case, you have other possible abstractions, namely that let's say you have let's say f and g are linearly independent real vectors. If you look at f plus ig, I is the imaginary unit as always, and f minus ig, then their moduli are the same, but they are not scalar multiples of each other. So this means that if f and g are living in some subspace, then the subspace will not do phase retrieval. So an example of this is that, let's say you do have f and g like this. If you look at the span of f and g in the three-dimensional space, then there are no almost disjoint pairs, but phase retrieval fails anyway. So again, for those who are maybe looking for problems to solve, we are not even close to having a complete list of abstractions to phase retrieval in the complex setting. So from now on, I'll work in the real setting, and again, maybe as a warm-up, let me give a couple of examples in the three-dimensional space. So this is I'm imposing here the infinity norm, but really the norm is not really essential. So first of all, let's look at the space as a subspace spanned by the first two coordinates, it's easy to see that it fails a stable phase retrieval from an example like this. But on the other hand, you can also look at the subspace consisting of all the vectors which are perpendicular to the main diagonal. So in other words, the vectors so that the sum of their coordinates is equal to 0. And I claim that it does stable phase retrieval with constant 2. So let's say we have two elements. So one way to approach this is to show that there are no almost disjoint pairs on the sphere. So let's say x and y are living on the sphere. We can always as far as x is concerned, we can always maybe change by changing the sign and renaming the coordinate. We can always assume that say x1 is 1, and then the other two coordinates will have to be non-positive, and their sum will have to be -1. So it leaves that either x2 or x3 has absolute value at least 1/2. And x1 also has, well, it has absolute value 1. So the conclusion is that out of the absolute values of x1, x2, x3, at least 2 of those 3 are greater or equal than 1/2. And the same is true for the entries of y. So it means that the minimum of x and y is at least 1/2. And now, by Bela-Kopytov's theorem, we are guaranteed to have a stable phase retrieval with constant 2. All right, so let's. So before actually going into the finite dimensional setting, let me briefly survey the results in the infinite dimensional setting. First of all, we don't have any hope that any infinite dimensional lattice will have an infinite dimensional stable phase retrieval. So for instance, if you look at the little LP space, then you can just play the gliding hump argument, which will produce almost disjoint pairs in every infinite dimensional subspace, so stable phase retrieval cannot occur. If you look, for instance, if you look at C of K spaces, then the situation is a little bit more complicated because it turns out that C of K, that the following three statements are equivalent. First, that C of K contains an infinite dimensional subspace with a phase retrieval. Second, it contains C0, which does stable phase retrieval. And third is that the counter-Bendixson derivative of the set K is non-empty. Well, what is the counter-Bendixson derivative? This is the set of the counter-Bendixson derivative of a set S is the set of its cluster points. So what happens here, we take the set of cluster points of K, and then for this set, we also find its own cluster points. And well, after these two operations, we have to have something non-empty. We also have some results about stable phase retrieval in LP spaces, but I will omit this for the lack of time. Now, what happens if you look at finite dimensional spaces? Then, it turns out that there exists a constant C, so that if X is an infinite dimensional lattice and K is a natural number, then there exists a K-dimensional E inside of X, which does phase retrieval, stable phase retrieval, rather with constant C. So C is a certain absolute constant independent of X and of K. So next, let's move entirely into the finite dimensional world. So let's say E is a subspace of a Banach lattice X, and let's say C is a certain fixed number. So E itself may not do phase retrieval, but the question is, does it have further subspaces which do phase retrieval? And if yes, maybe can we have a stable phase retrieval with constant C? So this constant C, I mean, it has to be taken to be sufficiently large and may be dependent on X. It turns out that in some settings, the answer is positive. So first of all, let's say X, our Banach lattice, is the space LPn when P is between 1 and 2. And let's assume that, kind of an extreme case, when E is a Banach lattice X itself. So then it can be shown that a random subspace of this LPn of proportional dimension does stable phase retrieval with a certain absolute constant. The proof, the proof is actually based. I should say that this is not entirely new. The case of P equal to 2 has already been known. It was established in the paper of Eldar and Mendelssohn in 2014, and the proofs are the idea of the proof that we have is to somehow look at a random subspace of proportional dimension and invoke Cauchy's version of Dvoretsky theorem that somehow if you take such a random subspace, then the two norm and the one norms will be in some ways equivalent. Well, and you can actually control the constant of equivalence. And the original proof of Eldar and Mendelssohn was different, but the idea also was to use something right. But the idea was also to use randomness. So what they had, they had what they called a random frame, a frame consisting of more or less random vectors, and somehow this worked for them. So what happens if we go into another extreme, and if we look at subspaces of L infinity n? Well, in this situation, well, it turns out that we also have we can also somehow guarantee the existence of subspaces with phase retrieval, at least on the in certain cases. So there are constants C1, C2, so that if E is a subspace of L infinity of dimension capital N, the dimension of its E itself is little n, then there exists a further subspace F of E, so that you can control the dimension like this, which does phase retrieval with some constant C1. So note that this theorem or this proposition only makes sense when little n is not too small. So of course, if this product here is less than 1, then like this is trivially true. Of course, you take a one-dimensional subspace and it does all the phase retrieval you need. But if it turns out that if little n is sufficiently large, then we can do more. We can do better. So, and in fact, we can say maybe a few words that this f that we obtain is a sufficiently nice copy of L infinity itself. And the way you build this capital F is you find almost disjoint vectors inside of capital E, and then somehow you build a suitable copy of L infinity on those vectors. Now, if you try to apply this theorem here, this proposition here, for E being L being the L infinity n itself. So if you try to apply little n, if you try to take little n to be the same as capital N, well, then the proposition here will give you the dimension of f to be the fourth root of capital N. Well, it turns out that you can do better. You can obtain a subspace of dimension square root of n. More precisely, we have the following. So for any k, there exists an isometry from L infinity k to L infinity of this dimension. So it's roughly k squared over 2, so that the image does a stable phase retrieval with an appropriate small constant. And it turns out that this result is in some sense optimal, because if you want to embed L infinity k into L infinity m without much distortion, and in such a way that the image will do a stable phase retrieval, then the ambient, so hold on just a second. So if the ambient lattice has the dimension m, then m will have to be quadratic with respect to k squared. And well, quadratic ambient dimension is what is guaranteed by the first part. So in this previous proposition, I mentioned that we want to, that what we are doing here, we are embedding L infinity of dimension k into some larger lattice in such a way that the image will do stable phase retrieval. And this gives rise to a more general problem. So let's say we have an n-dimensional E. We want to embed it into a lattice capital X of dimension capital N, so that the distortion is somehow controlled, and the image does stable phase retrieval with a certain universal constant. So again, we are starting with an n-dimensional, with a Banach space of dimension little n. We want to put it inside of a Banach lattice capital N of the smallest possible dimension. And a more or less trivial result is that you can always put things into L infinity of dimension, of exponential dimension. And the question is whether this is optimal. So the previous proposition shows that if you start with L infinity little n, then the quadratic dimension suffices. If you start with L2, then linear dimension suffices. But we don't actually know what happens for little L1. So we don't know what is the smallest dimension of a Banach lattice in which little L1 can be embedded in an SPR fashion. So to state my next result, I want to introduce the notions of p-convexity and p-concavity for Banach lattices. So we say that a Banach lattice is p-convex if this inequality holds. So just in case you wonder what the left-hand side means, well, as I said, you can visualize your Banach lattice as a function space. So in the left, your xi's are functions, and you perform the operations in a pointwise manner. And while we have p-concavity, if the opposite inequality holds, and we say that, if the first inequality holds not for all xi's, but only for disjoint ones, we say that we have an upper p estimate, and if the second inequality holds for disjoint vectors xi, we have a lower p estimate. And maybe as a way of example, clearly by the triangle inequality, any Banach lattice is one convex. So this first inequality here holds if you take p equal to 1, and infinity concave, both with constant 1, and LQ spaces, for instance, well, at least when infinite dimensional LQ spaces, they are p-convex for p less than or equals than q, and p-concave for p greater or equals than q. So why do I bring this up? Because these notions are actually helpful for finding further subspaces with stable phase retrieval. So the next proposition tells me that the first of all that, well, let's say X, our Banach lattice X, is p-concave with some constant p less than 2. Then for any E of dimension little n, there exists a further subspace F of proportional dimension, which does stable phase retrieval, and the constants here depend on P and on CP, the p-concavity constant. Now, on the other side of 2, the situation is not as nice. namely, let's say X is P convex with now parameter P greater than 2. So again, there exist constants K1 and K2, depending on P and CP, so that for any subspace E with dimension n, there exists a further subspace F of dimension, well, and here the estimate is only logarithmic, which does a stable phase retrieval. And if we have, as I said, this logarithmic estimate is somehow disappointing, but if you further assume some kind of a lower Q estimate, then we can actually get a polynomial lower estimate on the dimension of the subspace F. And from this formulation, and especially from the logarithmic estimate, you can guess that the proof actually uses Dvoretsky theorem, and it turns out that the F you obtain in this the subspace F that you obtain is going to be Hilbertian. So let me also maybe state a corollary about subspaces of it's a particular case of what happens in capital LP. So let's say P here is different from either 2 or infinity. Well, then for any F for any E rather of dimension of dimension n sitting inside of LP, there exists a further subspace F, which does stable phase retrieval with a certain constant, and then the dimension is linear when P is less than 2, and the dimension is polynomial in n when P is greater than 2, and this is actually optimal because, well, obviously when P is less than 2, you cannot have dimensions more than linear, and when P is greater than 2, then there's the subspaces of LPN which do stable phase retrieval, they will have the dimension no more than this. So this is optimal. Now I think I'll skip the proof because I see we are running out of time. And instead, let me maybe focus a little bit more on subspaces of capital LP and how we, if you start with a subspace of capital LP, how can you embed it into something in an SPR way? So the setup here, we are assuming that we are already having an SPR subspace of capital LP. And we want to embed it into LPN for some sufficiently small or reasonably small n. So specifically, we have the following. So let's say E is a subspace of capital LP for some measure, doesn't matter which does stable phase retrieval with constant C. So we are imposing here a technical assumption that C is at least 3. So E has dimension little n, and well, if P is 2 but well less than infinity, let's introduce this parameter alpha to be P over 2 plus 1. And if P is less than 2, then it looks like I'm imposing some kind of unnecessary complication. But this will appear actually a bit later. So let's say we have the numbers P and S. So S lies between P and 2, and E, in addition to being embedded inside of LP in an SPR fashion, you also embed inside of L sub S in some manner, not necessarily SPR. We are just assuming the existence of an isometric embedding like this. And in this situation, let's introduce the parameter alpha in this form. It's P over S plus 1. So here, so note that when P was greater than 2, then alpha was greater than 2 as well. In fact, the larger the P, the larger the value of alpha. Whereas if in the case of P being less than 2, well, alpha may be smaller than 2. In fact, if S is large compared to P, then alpha may be less than 2. So given this, we conclude that there exists a capital N, which behaves polynomially in little n. So little n is the dimension of E, and capital N behaves like little n to the alpha. So then we can embed E into LP of dimension capital N, so that the distortion of the embedding is controlled, and the SPR constant, well, it may be worse than what we started with, but only a little bit worse. So this permits us to embed into LPN in an SPR fashion. Going back to what happens in the second setting, so you can always, of course, take S to be equal to P, but if, as I said, if you can take S greater than P, then somehow your estimate on capital N appearing here will be better. I'm not going to prove this, but let me state a corollary of this. So let's say E is an n-dimensional subspace of capital L sub S for some S between 1 and 2. So 1 is included, 1 is excluded here. So then you can embed E into L1 capital N, and this capital N depends on little n only polynomially, so it's 1 over S plus 1, so that the embedding, the distortion is controlled, and the image of E does stable phase retrieval with some universal constant depending on S. The idea of the proof is that unfortunately there is a typo here. So it turns out that capital L sub S embeds into L1, and the typo is that here it's not P, it should be S. So capital S LS of LS embeds into L1 in an SPR fashion. And here again, I wrote using p-stable random variables. I meant to say s-stable random variables. So going back to this E, it sits inside of capital LS. You embed capital LS inside of L1 in an SPR fashion. So E now is going to be sitting in L1, and it's going to be SPR in L1. And now you use the previous theorem to reduce the dimension of the ambient lattice. So unfortunately, or fortunately maybe, this result requires E to be inside of LS for some S strictly bigger than 1. So you cannot do this for subspaces of L1. So for instance, we know that little L1 will not embed into capital L1 in the SPR fashion, and the same will also be true for finite dimensional L1s. So this kind of connects to what I said a little bit before. So we don't know what if we start with L1 of dimension n, we want to embed it in an SPR fashion into some Banach lattice, then I don't know, or we don't know, what is the minimal dimension of the ambient Banach lattice, whether we can do better than the exponential dimension. And finally, the last thing I want to mention is subspaces of, let's say our Banach lattice X is finite dimensional, and we want to look at at the largest possible subspace or subspaces which do phase retrieval. So there is this folklore result that if X is a Banach lattice and E is a subspace which does phase retrieval, then the dimension of X is at least twice the dimension of E minus 1. So again, this is this is true in the real case. In the complex case, things are more complicated. In fact, I think it's instead of 2 times the dimension, you have to take 4, but I'm not totally certain. I think I should present some kind of a proof, so this will be my victim. So let's say M is the dimension of the ambient lattice, and let's say its dimension is less than or equal than 2n minus 2, where n is the dimension of E. So let me, I of course forgot to like this. So let's see. Let's clarify what this little e means here. So let's say the dimension of X is less than 2n minus 2, and I'm going to show that in this situation, E must fail phase retrieval. So we know that a finite dimensional Banach lattice is the span of its atoms. So denote those atoms by, say, x1 up to xm, and for any subset A of our index set, let's denote by xa the span of the corresponding atoms. And let's say A is selected in such a way that its cardinality, as well as the cardinality of its complement, does not exceed n minus 1. So in this situation, we can find an element X in E, which is supported on capital A, and also we can find an element which is supported on the complement of A. And the reason such X and Y exist is that you just calculate the dimensions of the spaces involved. So for instance, if you take the dimension of A plus the dimension of X sub A, then it will be greater than the dimension of the ambient X, which guarantees non-zero intersection. And similarly, E does intersect X sub A complement, so this means that Y, like this, has to exist as well. And now we can say, okay, so the modulus of X plus Y is the same as the modulus of X minus Y, but of course, these two are not scalar multiples of each other. Also, we have this folklore result that this result is optimal in the sense that if X is a Banach lattice of dimension at least 2n minus 1, then the generic n-dimensional subspace will do phase retrieval, and therefore it will do stable phase retrieval as well. So it does stable phase retrieval, but, well, with what constant? So it looks like it looks like the constant will be bad. More specifically, we have this proposition that, well, let's say n is at least 5, so that we shouldn't deal with really small dimensions. And let's say E is an n-dimensional subspace of a Banach lattice X of dimension 2n minus 1. So really, everything is very tight. So the dimension of E is largest possible. Then if X, if here I meant to say E, if E does stable phase, well, if E does, well, if E does stable phase retrieval with constant C, then this constant C is at least roughly the square root of n. And if in addition you assume some kind of convexity, then you actually get something better. Well, hold on just a second. So here, here probably I meant concavity. For some reason, on the last slide, they have plenty of typos. So if you assume concavity, then you have a better lower estimate, but still it's kind of polynomial. And the question is whether you can do better than those polynomial estimates on the SPR constant. And I would like to finish my talk with this question. So thank you for your attention, and of course, questions are welcome.
Thank you very much. Questions, please.
Yeah, I have just some general question. Yeah, I know it should be Banach lattice, but is there analog in operators, for example, in von Neumann algebra, like SPR property? It seems we can also talk about disjointness, right? Is there any something like that? Yeah, I know in the complex case it's more complicated, but in operators also we have well-defined order, so disjointness.
So in operators, we've tried to look at this, and there are several obstacles. So first of all, we do have order, but we cannot find maximum and minimum. Further, we can talk about the modulus, but of course it somehow depends on whether you take x star x and then square root, or x star and then you take the square root. So I do not think that there are I do not think that there are really. I mean, you can ask the same questions, but somehow I don't think the same theorems will be true. Because for instance, how did this work?
Yeah, even in the complex case, we don't know. Yeah.
So even in the complex case, we know that there are abstractions because beyond disjointness, but we don't know what they are.
Yeah, sure. Okay, yeah. Thank you.
You're welcome.
More questions, please. Well, if there are no more questions, then we thank the speaker again. Thank you very much for the very interesting talk.
Thank you for the invitation.
So we shall meet again.
Yeah, well, see you next Friday.
Yes.
Thanks a
See
lot.
you. Bye.
Yes. Thank you.